which proton in this compound over here would be most acidic? So this guy, this dude, is a little bit tricky with what you need to know. What the pKa's that you should know by heart. Let's write those down for this problem. Right. So I got this down pat by now. And hopefully you do too by the time. Well, yep, you should have had it down in Orgo 1, in my opinion. So here is, right, pKa's for common compounds. RCOH, H3O plus, protonated alcohol. What are we missing? Protonated peroxide, yes. Okay, so these less than 0, around 0. This guy, carboxylic acid around 5, protonated amine around 10, water and alcohol around 15. Okay, and so if this R group is a benzene, it drops the pKa by approximately 5, right? So this guy is approximately 10, and that's this guy, right? And so when comparing it to the rest of these, so like for aldehydes, I mean, I don't think I recall any place in Orgo where we really consider losing an aldehyde at the H in an aldehyde acting as an acid. So for B, this H is on a carbon, a benzyl carbon. So we didn't really see that being acidic. We did see lots of examples in, I think, chapter 18 of the alpha carbon being acidic, right? And so this is kind of, you kind of need to know, I think, the relative pKa's of alpha carbons. So generally, this guy's, it's probably around 20, the pKa. Not that guy. This guy, right? You don't get to points around 10 until you have a carbonyl group on both sides of this alpha carbon. Once you do this with whatever you got on both sides, you start to get around 10, maybe a little more than 10, a little less than 10, depending on esters and amides on which side. But if you only have, if this is just a carbon chain on one side, or just in an R group that's not really special, it's going to probably be around 20 for this. So that's definitely below phenol. And these guys, right, B, D. I mean, we could, right, see how unstable the conjugate base is of these to show that prove that they're not acidic at all. Right, so at this point we know our answer is going to be A, but let's show the instability of the conjugate base for like D and B. Just let's try to do that. So here's D. If we pop off that proton, we're right here with a minus charge next to this guy here. So I mean, we could go like this, put the minus charge on the O, and then I mean we couldn't form a double bond here because that's sp3. There's really not much, no way to move this, to delocalize this minus charge away from the carbon. And I would expect same kind of deal for B. So that shows that the conjugate base is unstable, right? So if our conjugate base is unstable, that means this guy's unstable. So if this guy forms in solution, immediately it's going to change by picking up a proton and go back over here. So in solution, you'll just find the acidic form, the form with the hydrogen on it, right? So that would be for D. Let's see what B has for us. So, oops. Okay, BH. Let's see. If this guy popped off, we'd have a minus charge here. This is sp3, so it can't be delocalized to the right. We could form a double bond here, and we could just move this minus charge around our benzene ring, right? So let's see, so we put it there, we could move this here, and this here, and we'd end up, we couldn't move it on the oxygen because we'd break the octet rule. There's already 2 lone pairs, so we can't delocalize it past the ring. But so we'd have a minus charge all up in here. It's not very, still not very stable in the end, right? So we know A, right, is the best acid here.